Welcome everyone to my first class video on section 11. Now the pre-class videos, as you saw, right, we got a lot of the definitions and theorems out of the way, but this is a tough section. So in today's class video, I'd like to slow it down a little bit, talk about approximating with Taylor polynomials, and then talk about the error, Taylor's inequality, and how we can calculate out the error in using these polynomials to approximate things. And so let's go ahead and get to it. Again, we're trying to approximate things. And so I'd like to maybe start off this video by talking about maybe an old brute force way of approximating things. So here in example 16, I suppose, I sped up a video. I spent an hour trying to approximate the cube root of 140, right? And I sped it up so it's only 90 seconds video. But yeah, so, and basically it's just me taking guesses, cubing them, right? And then trying to get a better and better approximation. So let me go ahead. I'm going to play this video for you. It's very Inception-y here. Oops, I guess it's started a little bit mid. All right, so we're going to watch this video again. It's roughly 90 seconds long, me trying to find the cube root of 140 by hand. And I'm going to narrate kind of over it, what I'm doing, what are my steps, all this sort of stuff. And so first I prove a theorem about how to cube things quickly. I find out that the answer has to be between 5 and 6, and then I break that up even farther. So I say, like, what about 5.5? And I try cubing 5.5. And I find that it needs to be smaller than 5.5. And so then I say, okay, well, what about 5.25? And I just keep on breaking the interval in half over and over and over again. You can see right now I'm at, what, 5 and 13/64. Cubing that out. Now I did do this all by hand, so there's a decent amount of time here where I'm not writing things down, but I actually have a scrap piece of paper where I'm calculating out all of these fractions. And so that's what I'm doing here, is just trying to calculate out all these fractions, add them together, because I'm trying to compare the answer with 140. Is it smaller than 140? Is it bigger than 140? And it looks like in this case it ends up being bigger than 140. And so I know my guess was too small. And so then I would split the interval in half again. And so this is my final guess. This is, again, roughly an hour that I spent making this video. And then I looked up the actual answer. The actual answer was 5.19249410. And then I compared, right, how many digits did I get correct? And it looks like I have correct to the hundredths place. And so, okay, that's a pretty sad hour, all things considered, right? And then I zoomed in just to show you that it really was an hour that I spent doing this. Anyway, so yeah, this is the video that I created of calculating out the cube root of 140 by hand. And again, the big idea here is that we know that it lives somewhere between 5 and 6, right? Because when I cube 5, I got 125. And when I cube 6, you get 216, right? And so then you chop this interval in half and you say, well, what about 5.5? So 5 plus a half here. And we ended up finding out that this happened to be too big, right? And so therefore the answer should live somewhere smaller than 5.5, but larger than 5. And then we chop that interval in half again. So we say, well, what about 5.25, right? And we find actually that that ends up being too small. And so we say, well, therefore it needs to live, oops, wrong one. I meant to grab the highlighter. It needs to live somewhere in this smaller interval. And we keep on playing this game over and over and over again until we can figure out where, a decent approximation is anyway. And again, let me go ahead and write down my result. I have it pulled up here, 5.1953125 was the result. And the actual answer is 5.19249,410, so on and so forth. I'll say 10185 is what I wrote down in the video. There we go. So yes, we're just cutting, I'll write out here, cutting interval in half and cubing our guess. And then we repeat to get a better and better approximation. Okay, so I would like to show you how we can actually use Taylor polynomials in order to get a guess as well. And my claim is that this ends up being a bit faster. So this one I didn't make a video for or anything like this, right? We're just going to do this out by hand here in class. And so I would like to approximate the cube root of 140 using this Taylor series expansion. So this is something that we technically saw in section 10 of chapter 11, but then we really go into it in the first video there in section 11. So this is the pre-class video. Again, if you haven't watched those, I'd recommend pausing this video, going back and watching those first, and then going in and watching this video, right? Because, for instance, you should know what this choose, this binomial coefficient, the k choose n thing is. That's something that we went over in the pre-class video. So if that looks strange to you, please make sure you go back and rewatch that. Okay, so my first question related to this, right? If I want to calculate out the cube root of 140, a very natural thing to do is say, well, okay, since we were trying to use this formula here, we could say it's going to be 1 plus 139. That would be 140 altogether. And if I want to do the cube root of it, that'd be the same thing as raising it to the 1/3 power. And so kind of our first guess may be, well, let's try something like this. So again, you notice that your k is 1/3 and your x is 139. And I asked a very simple but maybe pointed question, will this work? Right? And the answer is sadly no. It will not work, and it all relies on this bit right here, the radius of convergence. This only works when our radius of convergence, right, is 1. So that is, we can plug in x values that are kind of 1 or smaller, and still you would have to figure out what exactly is happening at those endpoints of the interval of convergence. So the fact that we're trying to plug in 139, that's significantly more than 1, right? That is outside of our interval of convergence, and therefore, no, it will not work. So no, and the reason is because it's outside of our interval of convergence. Okay, well, again, we're supposed to be using Taylor series or Taylor polynomials in order to come up with a way to approximate the cube root of 140. So how can we do this? And the answer is with part B here. So I'm still going to use the same series expansion for the binomial series here. However, I'm going to do a bit of a trick, right? So I'm going to go ahead and split this off. And I found that, again, kind of there's a perfect cube at 125, right? 125 is 5 cubed. And so if I take this and I factor out 125, right? So I split it up, 125 plus 15, factor out 125, you should get something like this. And then roots, square roots, cube roots, kind of all exponents, right? They have this great rule that you can go ahead and break them up over multiplication or division. So I'm going to take the cube root of 125 and multiply it by the cube root of 1 plus 3/25. And so now, again, notice 5 is well known and understood and all this sort of stuff. It's just 5. But here, 1 plus 3/25, this now becomes a good candidate for x. Remember x, the radius of convergence, the things that we were allowed to plug in, right, between -1 and 1, right? So 3/25 is in that interval, and so now we have some hope. So let's go ahead and use this series expansion, and we're going to approximate, again, what is the cube root of 140 using this trick here. All right, so again, k is equal to 1/3, and now x is going to be 3/25. Okay, so let's just go ahead, and I want to first just use this expansion, and then I'll start plugging in some of these things. So we have, let's just focus on this cube root, or let me rewrite it with the 1/3 power. So I'm going to do 1 plus x raised to the 1/3 power for the time being, and then we'll plug in our specific x value here. And according to this series expansion, we're summing up, and again we have these binomial coefficients, k choose n, times x to the n. So the first one here, again, all of these, the k value is 1/3, so we're going to have 1/3 choose 0 times x to the 0, then we're going to have 1/3 choose 1 times x to the first, then 1/3 choose 2 times x squared, And right, normally this would just keep on going on and on and on forever, because we're summing up from 0 all the way to infinity up here. However, with these things, right, when we're doing an approximation, we're just going to stop after so long. So I'm going to maybe do one more of these. Again, if this was a quiz or an exam or something like this, they would have to say exactly how many terms they would want you to use. And in fact, I have at the end of this video or the end of this class here, I have a couple reasonable exam questions just to kind of show you what those would look like. Okay, so I'm going to go ahead and just use 4, and then therefore it's not really equal, but maybe I should use the approximately equal. So the first 4 terms will be approximately equal, but not quite actually equal. All right, now let's go ahead and start evaluating some of these things out. We saw in the video that anything choose 0, so 1/3 choose 0 is always 1. And we have x to the 0. Again, it doesn't really matter what x is. It happens to be 3/25, but that's fine. That's 1. 1/3 choose 1, right? That's going to be 1/3, according to, again, the video that we watched earlier. And then I'm just going to write x for the time being. And we'll go ahead and plug in our 3/25 here in our next line. All right, here's where it gets a little bit more insightful as far as what do these choose binomial coefficients look like. And remember, you start off with this 1/3, and then you drop by 1. So if you drop by 1, this is going to be -2/3. And you do this a total of 2 times. So now that we see that we already have the 2 numbers being multiplied, that's when we stop. And then you need to divide by 2 factorial. So notice we didn't really do this back here. It was just 1 factorial, which happened to be 1. So we didn't need that. And then we have x squared. Let's do another one here. This is going to be 1/3 times -2/3 times -5/3. So again, we're dropping by 1 each time. So we go from 1/3 to -2/3 to -5/3. And then we need to divide by now 3 factorial. So it's whatever this thing is here in the bottom. That's what the factorial is. In this case, 3. X cubed. And one more, and that should be enough. So 1/3 times -2/3 times -5/3. Keep on dropping by 1. We need 4 numbers being multiplied together this time. So what? -8/3 divided by, and 4 factorial, and then times x to the 4th power. Okay, now let's go ahead and start simplifying a little bit, and let's plug in our specific value here. So I'm going to do what this was, 1 plus 3/25. And we were doing the cube root of that. So, okay, 1 plus 1/3, and x was 3/25. Now, let's see. We have 1/3 and minus times -2/3. So that's going to be, what, -2/9. And it looks like we're dividing by 2 factorial. So 2 factorial is just the same thing as 2. And then x squared, so 3/25 squared. Next up, and again, I'm just kind of looking at the numerators here at my first go, so I see that that's going to be a positive 10 divided by 3 times 3 times 3 would be 27. And then I go to the denominator, I see 3 factorial, so that's going to be 3 times 2 times 1 is going to be 6. And then we're going to multiply that by x cubed, so 3/25 cubed. And last one, okay, 3 times 3 times 3 times 3, that's going to be 81 in the bottom here. In the numerator, let's see, we have 10 and then 8. So 80 on the top. It's negative because there's 3 negative signs there. And then we're going to have 3/25 being raised to the 4th power. Okay, now let's take another line to simplify. And notice that we want to take our answer and multiply it by 5 in order to come up with a full cube root of 140. So let's go ahead and take this, multiply it by 5. And try to simplify a little bit more. So, okay, we're going to have 5 times a bunch of stuff. And so 1 plus, and I can see the 3's are going to cancel here. And so I'm going to have, what, 1/25. And then minus, and it looks like I included 2 negative signs. Sorry about that. Should only have included that once. Probably were yelling at the screen. So we get a bit of canceling that happens there. So this is going to be 1/9. And, oh, I see there's a 9 on top. That's quite convenient. And 25 squared on bottom. So let's go ahead. I'm going to cancel out those 9s as well. And this is just going to be 1 divided by 25 squared. That's just how I'll leave it. Here, let's see. When I take 3 and I cube it, that's going to be 27. And I happen to have a 27 here in the bottom. That's quite convenient. And then 10 and 6 cancel a little bit, so that becomes 5/3. So I'm going to write 5/3. And let's see, I still have this 1/25 being cubed in the bottom. Fine. And then minus, and then same thing here, 3 to the 4th power happens to be exactly 81. And so I'm going to have 80 divided by 25 raised to the 4th power. And again, we're multiplying this all by 5. And so let me go ahead and, similar to our last video, right, I did a bunch of work, and we could even spend one more line simplifying things down. But I'm to the point where I'm relatively happy. I want to get a decimal approximation for this. And so I'm going to go ahead and plug this into my calculator and just see what I get. So when I do this, I get 243,398 divided by 46,875 here. Or that's the same thing in the decimal form as 5.1924 9066, and now it just kind of repeats. So the question is, well, is this good or not, right? And so let me go back up here. I'm going to cheat using a little bit of technology. Remember back here with this approximation, we had the 1 and the 9 were correct, but after that, we started going off by a bit. So let's go ahead and take this and see how we do with now our Taylor polynomials, which, by the way, has taken me far less than an hour to do. This has been way more enjoyable. And we can see we have the 1 and the 9 correct. We have the 2 and the 4, and we have the 9 also correct. So this is correct to 5 digits, or 5 decimal places here. And so actually we got a better result in far less time. And so again, kind of these binomial things, these are all thanks to Sir Isaac Newton. And so I have a quote that I was able to find online regarding these things. So he said, "I'm ashamed to tell you how many places I carried these computations, having no other business at the time. For then I took really too much delight in these inventions." So yes, Newton really enjoyed how fast you were able to do some of these approximations, much faster than some of the older methods, and certainly this brute force method that I had. All right, so now you kind of see the power of these Taylor polynomials. And so now I'd like to give you a shot at one of these. I'd like to approximate E using 5 terms. So now this is specifying how many terms to take it out to. So we're going to have the 0th term, the 1st, the 2nd, the 3rd, and the 4th. And those together would make 5 terms. And I'd like you to approximate E. So notice that you should probably be plugging in 1 for X. So please pause the video, give this one a go on your own, and then resume when you're ready to see the answer. All right, so here is my work. Again, this is asking for 5 terms. And so this is sometimes a point of confusion, that there's a subtle difference between saying a polynomial of degree 5 versus saying 5 terms. So when I say 5 terms, or when a problem says 5 terms, notice that it only goes up to degree 4, right? Because you have the 0th term, you have the 1st term, the 2nd term, 3rd term, and 4th term, right? And those added together, those are 5 terms. However, if it said a 5th degree Taylor polynomial, then you would want to take it to the 6th term, because that's when you actually see x to the 5th power. Okay, so I have my 5 terms. Notice I've plugged in first n equals 0, then n equals 1, then n equals 2, then n equals 3, so on and so forth. And in order to calculate out E, notice I plugged in x kind of immediately here. So I did my x was 1 in order to approximate E. And so I did this out 1 plus 1 plus a half plus a 6 plus a 24th, and I got 2.7083 repeating, right? So the 3's just keep on repeating there. And then I looked up the actual answer, right? So 2.7182818, and that keeps on going again on forever. So we can see that in a very short amount of time, we've gotten that it's 2.7, and then sadly at the 100th spot, we seem to be off. Although, interestingly enough, we did happen to get what the thousandth spot is an 8, so we're roughly off by 1/100th here. Okay, so this is how we can use Taylor polynomials in order to approximate values, right? Much faster than probably what we've been doing maybe before. And so let's go ahead and move on and start talking about, the complicated topic here, which is error, right? So when we do one of these approximations, as you can see, right, we're not going to be spot on. There's going to be some error. And so I'd like to talk to you about, right, how can we calculate out the error? And so before we get into Taylor's inequality, which we talked about in the pre-class video, I'd like to step back for a second and first of all, say what exactly is the error algebraically and what is the error graphically, and then we can use the Taylor's inequality to calculate out the error. So moving kind of through this list, again with finding the error explicitly using technology, then we're going to visualize it, then we're going to use that complicated thing, Taylor's inequality. So again, kind of numerically, what error is you take the absolute value of the true value, right? In this case, we were calculating out maybe E, minus the calculated value. So if I was to go ahead and apply this calculation here, before we were just kind of eyeballing it, but the true value was this 2.7182818, so on and so forth. That's maybe a good spot for me to stop. And then I'm going to subtract away what we got, right, which was 2.7083 repeating. And so when we subtract these things, and again, we can kind of go down 2 minus 2, 7 minus 7, 1 minus 0, so on and so forth, you'll see that we get the absolute value of 0.009948, and I'll round here to 5. And now the absolute values don't really come into play so much right here because it happened that our calculated value was less than the true value. But remember, the error should always be a positive number, so that's why the absolute values are there. So again, our actual error is a little bit less. It's just a fraction under, right, 1/100th. Just as we were eyeballing from before. We just looked at it and said, oh, the 100th place is off, right? So it's just a bit under 1/100th. That's what our error is. Okay, so this is grand and everything, but it assumes that someone else, right, we know what E is, right? And this is well documented and all this sort of stuff. But imagine, right, we're back in Euler's day, 1748 sort of deal, and we're calculating out E for the first time. And we do this approximation, right? There's no one to say, what this thing is. So, I mean, kind of, unless if you already have someone who knows what the value of E is to, whatever, 100 decimal places or something like this, then this method really isn't so viable. So, I mean, it's great for us to understand what the error is, but you can't just apply this kind of arbitrarily, right? You would need to know with great precision what the thing is you are approximating. That kind of defeats the purpose of the problem. Okay. So this one's kind of out. Again, kind of understanding what the error is, I went ahead and I've graphed here a nice little Desmos app. And so I'm going to click on this, and we'd like to approximate, again, the error between using our Taylor polynomial versus, this e to the x. All right, so here is my Desmos graph. I have e to the x graphed here. And then I've also included our Taylor polynomial. So let me go ahead and turn this on as well. And we can see that, notice that I haven't plugged in 1 everywhere I see an x yet. So this is actually approximating the full polynomial. And of course, we're very interested about e itself. So I would want to zoom in kind of around 1 here and see kind of how these things differ. And notice both of them are around 2.72, a little bit shy of that, right? And this difference right here, this vertical distance, and so now I've turned on the error, that visually is the error, right? So it's this vertical distance from our actual function, e to the x, to our Taylor polynomial, right? So the amount that it's off by, the amount that the output or the y value is off by, that is the error for our Taylor polynomial. So that's kind of visually what we mean by the error. Let me go ahead and switch back here. So where on the graph can we find the error? Again, this is going to be the vertical distance between our actual function, which in this case is e to the x, and the Taylor polynomial. And so we could see in this case, right, that the error didn't end up being very large, and right, relatively small, especially when we zoom out and everything. We can see that actually that this was a relatively small error, and we even saw, right, that it's less than 1/100th. So the length of that line right there would be less than 1/100th. So again, this is great for our understanding of what error is and how can we visualize it graphically. But still, we need to know a lot about e and e to the x in order to viably be able to, calculate the error using this method. So again, it's not really great either. All right, so here is the big content for the day, Taylor's inequality theorem. We'll see we only need actually very little information about e in general in order to see how much our approximation could be off by. So again, this is saying, right, if you use a Taylor polynomial of degree n to approximate a function's value, that the error is at most this value right here. But this is rather complicated, right? And it takes a little bit to digest this. And so I'd like to go rather slowly, step by step, in figuring out what each one of these values are, what they mean, right, and how we can find them. And so I'd like to use our particular problem that we've just done. And just kind of an FYI with all theorems, right, they are theorems, right? They have proofs. So it's nothing that's, right, where do all of these things come from? Why is the formula the way it is, right? These questions quite often are answered by the proof. And so if you're at all interested, I mean, it is quite complicated and it takes up several sheets of paper and everything, but this theorem does have a proof of why it is the way it is. And so if you're at all interested in that, feel free to watch that video, maybe after this one. All right, so I'd like to go through this using my results from example 18, and I'd like to fill in the blank sort of deal. What is a, what is n, what is d, what is m? What are all of these things, all of these variables that we have here, and what do they mean? Okay, so starting off with a here, what are our values for a and n? So remember, a comes from, well, 11.8, in fact, is where we first saw something like this. A is supposed to be the center of our Taylor polynomial, of our Taylor series, right? N is supposed to be the degree for our approximation, right? We didn't continue on forever. We stopped with some finite polynomial, right? We didn't use the infinite polynomial. So what was the degree of that polynomial that we used? So if you recall, right, we had 5 terms, or this was a 4th degree Taylor polynomial. And so n should be equal to 4. As for our center, remember, this is the stuff that's usually like an x minus a sort of deal. And you probably recall, and we'll zoom back up here really fast, right, that for our Taylor polynomial, right, we had x minus 0 raised to the nth, right? It was actually a Maclaurin polynomial. So our center here is at a equals 0. So that's where we can find these values. Next up, right, I have a question about what should the value of d be so that x equals 1 is in our interval. So remember that we wanted to say something about e to the first power, right? We were using our Taylor polynomial to approximate e to the x, and we were very interested at x equals 1, right? We wanted to plug in 1 everywhere we saw an x. And there's this whole bit, right, that if you want the error that this Taylor inequality gives us, right, we want to make sure that our x value is actually in this interval. And so we need to explore a little bit what this interval actually is, right? It seems like it's centered about the center. That makes sense, right? So it's a minus d and a plus d. So, and d quite literally stands for a distance away from the center. So if our center is 0, And for instance, this is d over here, and we do a minus d. So we've gone negative d this way, we've gone positive d this way, right? And then maybe I'll use green here to say that this right here would be this interval, in our case, from 0 minus d, because our center is 0, to 0 plus d, right? And we want to make sure that x equals 1 is in this interval. So that way our conclusion actually says something about approximating when x is equal to 1. And so if you wanted x equals 1 to be in your interval, the best way to probably do this, right, and not to waste anything or anything like this, is to just have distance equal to 1, right? So if you just go 1 over, that's fine. That gets 1 in your interval, and you don't go beyond this. And usually you want to choose maybe the smallest interval in order to get the best error approximation. So I'm going to choose d is equal to 1, and in which case our interval that we're ranging between is from -1 to 1. So notice that it stays centered about 0, but now it includes x equals 1 in this interval. So now we know what our d value is. And this becomes quite important for the last step, which is the most confusing, I would say. Find the value of m. So here we have m in the numerator for this whole thing. And m is the only one that you can't really just look at the function of the Taylor polynomial and just grab it sort of deal. It requires a little bit of work. And so here's the statement for how you can find m. So m, this capital M, quite literally, you should think of it as the maximum, right? So we want capital N to be the maximum of not just the function itself, but actually the n plus first derivative. Notice you have a lot of n plus 1s sprinkled around here, right? N plus 1 factorial, n plus 1, right? So it's the n plus first derivative of f. Okay, so if we know this, right, the n plus first derivative of f, we want the maximum value that this takes on this interval that we've now found, right? So x ranges from -1 to 1, and we want to make sure it's the maximum for all of these x values. So that's quite important. Okay, so the first step is that I need to take n plus 1 derivatives of e to the x. Now remember that my n is 4, so I need to take 5 derivatives, n plus 1, right? It's going to be 5 derivatives, fifth derivative. And our function, remember, is e to the x. So f of x is equal to e to the x. So if I take one derivative of e to the x, I get e to the x. If I take a second derivative of e to the x, I get e to the x. And of course, right, as we continue to take derivatives, well, the derivative of e to the x is always e to the x. And so even if you take 5 of these things, you will still have e to the x. And so we want to make sure that we have m should be the maximum value. And it turns out our fifth derivative of our function happens to be the same thing as our function anyway. But what I typically do here is now I graph this. Hopefully it's relatively simple, but I'd like to do a quick sketch of the fifth derivative. So in this case, e to the x, and it looks something like this. And we want to make sure that we have the maximum value, right? M needs to be the maximum value for this function on our interval. So remember, our interval was from -1 to 1. So we're kind of looking in this region right here. And I want to know what is the maximum value that this fifth derivative function, e to the x, takes on this interval. And we can see over here on the left-hand side, well, that would be e to the negative first power is what it's outputting. It's a positive number. It's fine and everything. But I think, for instance, over here, it gets a little bit bigger. Right? E to the 0th power is 1. That's a little bit bigger according to this function. But you can notice that the maximum on this entire interval actually lies over here on the right-hand side. That the maximum, this capital M value, is going to be e to the first power. This is the most that the fifth derivative ever is on this interval from -1 to 1. So in our case, m should be equal to e to the first power. All right, and with that, we now have all of the pieces that we need. We have the m value, we have n, we have d, we have all this sort of stuff. We're going to put it all together, and we're just going to use this fact that we know that, again, relatively little about e. We'll only know that it's between 2 and 3, and we're going to come up with what the maximum error is for e to the first power, right? So according to this, we already did our approximation. Again, that was way back here. So our actual approximation was this 2.708333, right? And we cheated. We looked up and we figured out what the actual answer was, right? We saw that we were off by roughly 1/100th, but we're going to pretend for the time being that we couldn't look it up, right? We want to know, maybe blind, how good is this, right? And so, okay, here's what we can say. According to Taylor's inequality, our approximation is at most off by, and again it goes m divided by n plus 1 factorial times x minus a to the n plus first power, right? And so we're going to start plugging things in. We know that our m we found to be e. We know that we had our n to be 4, so 4 plus 1 is going to be 5 factorial. We have x minus, our a value was 0, and we're going to be raising this to the n plus 1, that's going to be 5th power, right? And so if we wanted kind of the worst case scenario, and I could simplify this down a little bit more, e divided by, and 5 factorial, 5 times 4 times 3 times 2 times 1, that's going to be 120. And now, if we wanted to get just a number out, right, rather than this, again, just like before when we took like the maximum, the worst case scenario for this fifth derivative, we could also do the same thing here, right, and say, what is the worst that this could be? Well, x on our interval is ranging between -1 and 1. And if we take that and we raise it to the 5th power, well, you can think about what's going to happen and notice that there's an absolute value here. But if you take it relatively close to 0, right, and raise it to the 5th power, well, that's going to be 0. So that's really not the worst case scenario. Really, the worst case scenario is going to be when it's closer to 1, right? 1 or even -1 because of those absolute values. So basically, the farther away from 0 it is, the worst case scenario it is. And so the maximum error that we're going to have here is going to be e divided by 120, and then something like 1 to the 5th power. Again, those absolute values aren't doing a whole lot. 1 raised to the 5th power is just going to be 1, and so you just get e divided by 120. And we know, right, this isn't so great because, right, it has e in it as far as what the error is. So we're going to use this fact that e is at most 3. So we're going to say that this is less than or equal to 3 divided by 120, which ends up being 1/40th. So remember, our actual approximation, right, was off by really closer to 1/100th. That was actually a little bit less than that. So Taylor's inequality is not perfect, but notice we do not need to know a whole lot in order to confidently say that it is certainly off by at most 1/40th. So this is kind of what Taylor's inequality gets us. Okay, so that's kind of the slow version through very carefully identifying each one of these pieces. I hope that this has been useful. I have 2 more problems. Like I promised earlier in this video, right, I have a couple of problems here that I think are quite reasonable for quizzes and for exams, things like this. And so I have them in multiple choice form. This one here, the 3rd degree Maclaurin polynomial for sine, suggests that sine of pi over 6 is approximately equal to 0.49967, so on and so forth, right? And of course we know sine of pi over 6, this is actually on the unit circle, so we could actually say we know that it happens to be 0.5, just FYI. But I want to use Taylor's inequality to see what is the maximum error possible for this approximation, right? What does Taylor's inequality actually tell us? And so I'd like you to pause the video, right? We've gone through everything step by step back here. Try to use Taylor's inequality, identify all of these pieces just like we did back here, right? And try to apply it to this function sine. All right, so please pause the video, give it a go, and when you're ready to see the answer, come on back. All right, so here is what I've come up with. If you got the correct answer, D, excellent job. But let me walk through kind of step by step where I was looking and what I was thinking about when I answered this question. So the first thing that I noticed that it says we're going to use the 3rd degree Maclaurin polynomial. So 3rd degree, that's telling me that my n value should be equal to 3. It's a Maclaurin polynomial, and so therefore we know that a is going to be equal to 0, right? Because Maclaurin polynomials are always centered about 0. That's kind of the definition of these things. Our function sine of x, so I now know what my function is. And I want to say something about this function's value at pi over 6. So kind of moving on to what was part B for our last example, trying to figure out what should the d value be, so that way, the Taylor inequality actually talks about pi over 6. And so if I want to include pi over 6 in my interval, and we're centered about 0, then it would make sense that I need to be able to step away, right, a distance of pi over 6 from my center. So d should be equal to pi over 6 in this case. And now finally, the most complicated bit, right, this m value. So the m value, we need to take n plus 1 derivatives, right? So when I take n plus 1 derivatives, well, notice my n is 3, so I need to take 4 derivatives. So here's the first derivative of sine, second derivative, the third derivative, and the fourth derivative. And notice for fun, we actually got right back to sine again. And we want to know, where is sine the maximum, right? What is the most, what is this capital M value for our fourth derivative, which happens to be sine. And so I went over here and I drew a picture for sine. And I saw on this interval, again, we're just interested between negative pi over 6 and positive pi over 6. So from negative pi over 6 to positive pi over 6, so a lot I was forgetting about here. But just on this interval right here, it looks like the biggest that it ever gets is at 1/2. And actually, this is a fine time to also bring in, right, I didn't mention it in our last problem because it happened to be always positive. But if we look carefully at the statement for Taylor's inequality, right, notice that actually there's some absolute values there. So you would actually want to look at the smallest and largest if you get some negative numbers and see what's going to be the overall largest once you take those absolute values. And so let's go back here, and I'll just show you that, again, it doesn't happen to matter in this case. So the largest positive value here is going to be 1/2, right, over here on the right. And then also if we looked all the way over here on the left, this is where sine is actually equal to negative 1/2. So once you apply those absolute values, in this case, you would get the same result either way. Okay, so now we go ahead and we plug things in. So instead of m, I plug in 1/2. Instead of my n plus 1 factorial, right, again, n was 3, so I'm going to do 4 factorial. And then I'm going to have x minus my center. I found out that my center was 0. So x, the absolute value of x raised to the 4th power. And again, kind of the worst case scenario, if we want to get a number out, which obviously all of these here are numbers, right? We don't want to have any x's in there. And again, we were interested in approximating at pi over 6, right? So that's kind of as far as we can get away from 0 in this interval. And so, okay, we have pi over 6 raised to the 4th power. And so this is the maximum error that we have in using the third degree Taylor polynomial to approximate sine of pi over 6, which again, we all know is 1/2. And we can see that, yes, this is off by a bit. Okay, so the last one, I have another kind of style of question here where it's not asking you to evaluate at a specific value, but rather an interval, right? So the question goes, according to Taylor's inequality, what is the maximum error possible in using the second degree Maclaurin polynomial? So again, we can see here n is going to be equal to 2. The fact that it's saying a Maclaurin polynomial, apparently I forgot the r, sorry about that. Maclaurin polynomial, we know that a is going to be equal to 0 for the natural log of x plus 1 in this particular interval, right? And we want to know what is the maximum error. So again, we need to go through. We need to find out what is this m. We know n already, so we know there's going to be a 3 factorial down here. We know we're going to have x minus a raised to the n plus 1st power, so raised to the 3rd power. And so again, we need to kind of play this game. We need to calculate out our m value. Let me just say, right, maybe because m's the hardest thing to do, why don't we go ahead and simplify this a little bit first, right? We know kind of worst case scenario is if we were farther away from our center. So of course, 0 cubed is going to be just 0. So the farthest we can get away is going to be at 1/2 or negative 1/2. When you take the absolute values, it won't matter. And so we're going to have m divided by 6, that's 3 factorial, and then times 1/2 cubed. So notice I chose the one that was positive, so the absolute values weren't really doing a whole lot. So here we know that this is, okay, 6 times 8 is going to be 48. And so now we just need to figure out what this m value is, and then that will help us get this final answer. So now we need to take several derivatives, right? We were using a second degree Maclaurin polynomial, so we need to take 3 derivatives. So again, f is this natural log of x plus 1. Let's take one derivative. We're going to get 1 over x plus 1 times the derivative of the inside just happens to be 1. So there we go. Let's take a second derivative. Oops, forgot my x's there. So a second derivative. I'm going to rewrite this really quick. This is the same thing as x plus 1 raised to the negative first power. So if I take a second derivative, the negative 1 is going to come down. We reduce our power by 1, and then we multiply by the derivative of the inside, which happens to be 1. Okay. And then finally, our third derivative. And this is where we get to stop. Well, the negative 1's along for the ride. When I take the derivative of this, a negative 2 comes down, and I get to reduce my power by 1. So I get x plus 1 raised to the negative third power. Let's go ahead and simplify this down a little bit. We're going to have 2 divided by x plus 1 quantity cubed. So this is our third derivative, and remember we're very interested in that for calculating out our m value. And my next step would usually be to draw a picture of this. So if I draw a quick picture, let's see here, I'm going to do it in maybe purple or so. I guess I didn't really talk about my d value yet. We know, I guess I kind of just skipped over this, right? But I wanted to include negative 1/2 to 1/2. So negative 1/2 to 1/2, and we were centered about 0. So this is just saying that our d value should be 1/2, right? We need to be able to do 1/2 this way and 1/2 this way. So okay, our d value should be 1/2, and we're very interested on this interval from 1/2 to negative 1/2. So now I need to do a small sketch for this function here. And let me kind of move this over because I know that this, right, there's a asymptote at x is equal to negative 1. So if I was to extend this way right here, at negative 1 there's going to be an asymptote. And otherwise this looks kind of like the standard reciprocal function, but it's more extreme because we have this cubed going on here. So if I was to do a sketch of this, we'd get something like this. And then down here again you'd have, kind of the other piece. But we don't really care about that. We only care about on this interval from negative 1/2 to 1/2. And so you can see this one's a little bit different, right, than maybe some of our previous ones. It's actually a decreasing function. And so if we were to plug in some values, for instance, if we were to plug in negative 1/2, we can see that this actually gives out the tallest value, the biggest output, right? And so let's just verify this. We have 2 divided by negative 1/2 plus 1 quantity cubed. And if we were to evaluate this, we'd have 2 divided by 1/2 quantity cubed. And so if I take 2 and I cube it, I get 8. So 2 divided by 1/8. And if you go ahead and instead of dividing by a fraction, you multiply by its reciprocal, you're going to get 16. Now this in comparison to right here, for instance, if you were to plug in 0, you would get out 2. So this is 16, then you have 2, and if you were to plug in 1/2, it's smaller still, but you kind of start getting some fractions and all this sort of stuff. So the maximum value is actually on the left-hand side now. Before we had some coincidences, right? It always happened to be on this right-hand side. This right-hand side. So I wanted to make sure to include one where this m value was not just always on the right-hand side. It can actually be on the left. It could even be in the middle. So you do really have to draw out a picture and look for it. So in this case, our m is 16. Let's go ahead and substitute that in. Instead of m, let's write 16 here. And that's going to be, 16 divided by 48? That's going to be 1/3. So the error is at most 1/3 according to this, and that happens to be answer B. All right, guys. Good luck on your homework and everything, and I'll see you next time.